Well, my student, today we shall start going into the broad subject content under the head Electronic Properties 1 as it is mentioned in your syllabus. Now, this broad subject head mainly we are going to discuss about the electrical conductivity in solids. Okay? So mainly we will try to discuss about the electrical conductivity in solids. Specifically, we shall start with the article of Boltzmann equation and its consequences. Okay, so Boltzmann equation and its consequences. Presently, this article A will be discussed in three parts. Part 1 will be introduction, and internal scattering. Internal scattering events. In part 2, we shall talk about the derivation of Boltzmann equation. Derivation of Boltzmann equation and relaxation. Time approximation. Okay? In third part, we shall talk about the consequences. So, consequences in different cases. Well, so our main subject matter is the Boltzmann equation and its consequences, which will be presented before you in three parts, and the parts are these. So, we shall start from the part 1, we shall talk about the introduction of such phenomena and your internal scattering. Let us start with that. So, our first part is to discuss about something introductory of these topics and some internal phenomena, specifically as I mentioned here as internal scattering event. Okay. Basically, the Boltzmann equation describes the non-equilibrium distribution in presence of external field and internal scattering. So what I'd like to say, the Boltzmann equation describe the non-equilibrium distribution in presence of external fields. The fields may be your electric field, magnetic field, or the both. The presence of external fields and scattering. Well, so this is the basic, the most important characteristics of this Boltzmann equation. We shall go into detail stepwise. So here I just highlighted a few words about this Boltzmann equation. So now, as there is the external field and also internal scattering, now let us first of all talk about the internal scattering. So first of all, let us talk about the scattering of electrons in bands. Well, now whenever we think of the motion of an electron inside a crystal, it is quite natural, and we know all that the electron experiences too many collisions, not a single, too many collisions during its motion or passage through the crystal with the positive ion core mainly. And that positive ion core is the basis of the lattice structure. The crystal structure is formed by the positive ion cores. So, in presence of external field, maybe electrical or magnetic or both, the scattering of electron during its passage through the positive ion cores becomes very important fact. And we know all that this will contribute, or this scattering of electron will responsible for the resistances. So it has an important role its role is manifested. Its role is manifested in electrical resistance. Okay. So this is very quite natural that during the motion of electron inside the crystal lattice, the scattering phenomena comes into play. And that phenomena has an important role in developing the resistance, which is called the electrical resistance. Okay? So, now we shall discuss about the internal scattering, and let us do that. So we are going to discuss about now the internal scattering. Now let us mention or recall one very important fact and finding, that Drude in 1900 with his free electron model assumed that electron scattered with the positive ion core only. So only there is a scattering phenomena of the moving electron with the positive ion core. It was the Drude proposal. And with this assumption, he estimated a mean free path between two collisions of the order of 1 to 5 angstrom. Okay? But what is observed experimentally? experimentally for many metals, for most of the metal, at room temperature, this mean free path length is of the order of 100 times larger. So it's a point of consideration, an important point, that experimental value is high enough compared to our Drude model. Later, this phenomena, this discrepancy, has been addressed due to the neglect of other scattering events. Besides this only single type of scattering, there may be some other sorts of scattering, and due to that neglect of that effects, this discrepancy arises. Okay. Now, quantum mechanically, this discrepancy was addressed through the perturbation to stationary block wave, and block wave represent the electron. So, quantum mechanically, the discrepancies is addressed through the perturbation on stationary block wave. Because of the fact that whenever a moving electron inside a crystal is very near the scattering centers or scattering potentials, whatever it be, the incident wave representing the electron, that is a Bloch wave, must be distorted, and so it is treated through perturbation theory. Okay? And it was found that the perturbation comes in three ways: during scattering, the three ways are: one, the scattering from lattice defect, the second way is due to scattering from lattice vibration. Lattice vibration or phenomena. And thirdly, it is due to the electron collision. Okay, so these are the three types of scattering that we shall discuss to some extent elaborately before going to the derivation of Boltzmann equation, right? Let us discuss all these three events one by one. So first of all, we will try to discuss about the scattering due to lattice defect. So scattering due to lattice defect. We all know that lattice defects may be vacancies, it may be dislocation, may be impurities. So vacancies, may be dislocation, or it may be impurities. Now, whatever be the nature of lattice defect, once the defect is assigned inside a crystal, it becomes a permanent structure. So, to a moving electron or to a Bloch wave, this defect appears as a static scattering centers. So it is time independent. Time independent interaction will be time independent interaction, as well as during this time independent interaction we may think that this lattice defect, which means is a lack of strict periodicity. Lack of strict periodicity arises for these three types of facts. Now, when the Bloch wave came to interact with the defects, that interaction will be static time, that is time independent. It is elastic. Elastic, it is point scattering, I mean the scattering occurs from point. So this point scattering, it is time independent, elastic. And also we can call it this type of scattering is called as simplest in nature. So, for the time being, we can consider only these main features for scattering due to lattice defect, or scattering arises out of lack of strict periodicity in your crystal lattice. Now, our second point is your scattering due to lattice vibration or phonon. Right? We all know that due to thermal vibration, what we can expect? That the strict periodicity is deviated and the deviation, it depends on time, or maybe the deviation is time varying. And as a result, due to thermal vibration, the ionic crystal, when gets deviation from its static periodicity, the electron will experience or encounter some sort of collision or scattering event, and that event is called the lattice vibration, the scattering due to lattice vibration. And this is actually is not static. It is not static event. It is time dependent. So with time, the situation may vary. As we have told you, we have discussed in the scattering due to lattice defect, it was elastic type of scattering. Now here we will observe the phenomena as inelastic condition. The most important one is that this scattering phenomena is most dominating. So it is called the most dominating or most dominant feature or most dominant event, and it is responsible for DC resistance. Okay. So In the first point, we talked about some static event where electron collides with a static pattern of ionic positions. But in this case, the electron encounters such collision when the static periodicity is not be there. It will vary with time due to this thermal vibration. As a result, the collision is called time dependent, and we shall discuss you later in a more elaborate way. Then we can see that this event cannot be considered as an elastic one. It is inelastic. That's when the energy of the incident electron will not be conserved by its own. It has to be conserved with some other system when taken together as a whole. So it is inelastic, and we should keep in mind that this event gives the major part of DC resistance. So it is the vital event. It is time dependent, at the same time inelastic. Okay. Next, we will discuss about the third point. That is the third source of scattering. Due to electron interaction. So electron-electron collision, and students should keep in mind that this is an important phenomena, important event beyond your independent electron model. Independent electron model. In case of independent electron model, this type of collision was neglected, and here we are going to focus this third type of collision, which is electron-electron scattering. But in fact, it is very negligible. Both at very low temperature as well as at high temperature. So whenever we pass into high temperature, the other conditions become more frequent and important. But this effect is very much insignificant. Also in low temperature, this type of interaction has no considerable effect. Okay. So we just talk about briefly the three sources of scattering that we can take into account while discussing the electrical conductivity in solids. Now from a different point of view, so Paris principle that the electrons in solid may be treated as non-interacting we know that despite of high electronic density, the electrons are treated as non-interacting. So despite their high density, right? So finally, what we can conclude? So finally, we can conclude that only two types of scattering. One is your due to lattice defect, and secondly due to lattice vibration or phonon are important. As regard the electrical conductivity of metals or solid, right? So we have just highlighted the basic points on the three types of scattering centers. Depending upon this knowledge, we shall now pass over to our next important task for derivation of Boltzmann equation. Well, now let us see how such scattering effect can be estimated quantum mechanically. We have mentioned that quantum mechanically the scattering effect will be estimated through perturbation theory. So the probability of an electron in a state psi scatters to another state psi k prime can be written as, say, W k prime k. So W k prime k is the probability for an electron in state psi k which will scatter to another state psi k prime. K prime, H prime, K, square modulus of that. Now this can be written also in this way. Integration over here psi k prime star H prime psi k and square of this two, of this integral, where H prime is your perturbation. To Hamiltonian. That is equivalent to your the scattering potential or interaction potential. So H prime is the perturbation term. Now if we write this psi k in log form, that is psi k can be written also in this way, UKR e to the power I k dot r in Bloch form, in Bloch wave form, right? So if we replace this psi, then our observable, the W k prime k, can also be written integral UK prime star H prime UKR and with your e to the power I k minus k prime dot r, right? Of course, this H prime, the interaction potential, may or may not be time dependent. So it may or may not be time dependent, right? So we have to discuss about something case-wise, that how the H prime will look like and the relationship of energies that has to be discussed now. Let us mark the equation as 1 and this equation as 2. Now, with the choice of H prime, we will have a different W K prime K value. So let us see how it will look like for different cases. For lattice defect, that is scattering from lattice defect, it is your static event. So for which our Hamiltonian must be time independent. So H prime, which may be in general the function of R and T, but for this static event, I mean the scattering with lattice defect type of scattering, then the H prime will be time independent. So H prime is the time independent. And for static event, we have mentioned that the scattering is elastic. So as the scattering is elastic, so energy E must be equal to, energy with specified K and energy with K prime must be equal. So this is the case for static event, which we call the elastic also. And if it is elastic, then energy relation will be this. So energy is constant. Energy is constant. Right? So it is the simplest one. The simplest case. Next, we shall pass over to the second case for scattering from lattice vibration. So now we are going to talk about the scattering from lattice vibration. Or phonon. We all know that scattering from lattice vibration or phonon, the phenomena is time dependent. So H prime should not be time independent as it was the case for elastic. So it is time dependent. So H prime would be time dependent. So as the scattering is inelastic, the energy relation, as we have mentioned just now, for the case of elastic, it was Ek equal to K prime, but it should not be for this case, right? But the energy relation can be written in other way to make the conservation law satisfied. So we can write in this way that Ek prime minus Ek must be equal to h cat omega being characterized by Q vector, where Q characterizes the phonon wave vector, right? So energy relation will be this much for the conservation of energy. So this is the energy relation. And where Q is the phonon wave vector. Okay. Now, because of this phonon, the H prime must contain a special dependent factor of the type e to the power I Q dot R, which implies that we can write H prime in this way, say some factor H1 into I Q dot R. So for scattering with the phonon, the perturbation Hamiltonian can be represented in this way, where Q characterizes the phonon wave vector. So naturally there will be a matrix element, so W K prime K must have a matrix element of the type K prime H prime K, which can be written in this way: integration over dk dr u k prime star h1 u k to the power I k minus k prime plus q dot r. Okay, so we can expect such an integration which is the matrix element. So this will be the form for our inelastic collision associated with the scattering of electron with phonon. Now we can also write this expression from here. We can write a relationship in terms of the reciprocal lattice vector G. Now we may arrive, or we may set k minus k prime plus q plus reciprocal lattice vector G to be 0 in order to have a non-vanishing matrix element. For non-vanishing Wk prime k. Okay? So from this relation we can write in this way that q plus g is equal to k prime minus k, which is an important relation which involves, or which you come across in case of scattering with the phonon. The G is called the reciprocal lattice vector. Now let us come to discuss about the last case of scattering phenomena, which is electron collision. We have mentioned just before that this electron-electron collision was neglected in our independent electron model. Though it is a fact that electron-electron collision may be important, and this type of collision involves the Coulomb repulsive potential. So this is your H prime, and for this the topic, the analytical part is very difficult, but in practice it is found that electron-electron scattering effect is very negligible. So here in this case, in our today's class, we will not go into details of this electron-electron collision. Only we should like to mention that a Coulomb repulsive type of potential will be involved, and the analytical part is not so easy. And in this case, the energy conservation relation would look like this. That energy relation would be, say, E1 plus E2. I mean, when electron 1 is interacting with an electron 2, the energy will be readjusted in such a way, say it is your E1 prime, E2 prime, right? So this will be the energy relation. This will be the potential, I mean the perturbation potential. And now we have found, we mentioned that it is found experimentally that such collision is very insignificant. So we are not interested to go into details of this difficult mathematical part. Now, one thing we can also mention from a different point of view. So from a different point of view, that is, from Pauli's exclusion principle, we say that the electrons are non-interacting. Electrons are non-interacting. Interacting Fermi gas. So what does it imply? It implies that the electron-electron collision cannot be occur or cannot occur in case of the electron-electron collision. If we like to consider the electron-electron collision, that phenomena will not occur due to Pauli's exclusion principle. The interesting fact is this: they are non-interacting in spite or despite of high density. Even we know that in case of any metal or conductor, the free electron density is very high, but still they are non-interacting. And because of this, the electron-electron collision can be neglected. So this is called the different point of view. So in this way, we like to close the discussion over the internal scattering phenomena, while the electron moves inside a crystal under the influence of external field, right? Recap. Now let us recap what we have been discussing about the internal scattering. So we are now going to recapitulate. we have talked about the scattering, that how many types of scatterings are there and what are the relative consequences that arises when electron passes through the crystal. Also, we have given hints how to estimate such scattering effect quantum mechanically using perturbation theory. So, we have talked about the types of scattering event. Its consequences, we have found, we have given a hint to calculate such scattering event through perturbation theory. And in doing so, we have discussed very little though about the Hamiltonian, part of Hamiltonian. It may or may not be time dependent. Time dependent, right? And we also told a very little is told about electron scattering. We have told you that this scattering poses some formidable complication in solving the solution, and for that we have mentioned that because of Coulombic interaction, Coulomb repulsive potential, and two, there's a many body problem. So because of these two main features associated with such electron-electron scattering, it becomes very difficult to go analytically. So it poses formidable complication. Okay. We have also mentioned that the effect of such scattering in relation to the conductivity of electron or the electrical conductivity in solids, the effect is very minimal. I mean, it is insignificant. So we discarded to talk much more on this point. But one should keep in mind that there are much more things to talk about this point, and we shall come across as and when it will be required, right? So let us leave it now for the time being. So this is all about the internal scattering phenomena that an electron experiences during its passage through the crystal lattice. Now, after having this knowledge about the internal scattering, we will go over to our second part. So here is the end of our first part. Okay.